Chapter 11. Here we see a crystal of vitamin C. Vitamin C is also sometimes called ascorbic acid, which meant without scurvy. Because if somebody didn't have vitamin C, they would get scurvy. Scurvy is a disease of the connective tissue. Vitamin C is necessary to hydroxylate proline residues on the amino acids of collagen. And if they're not hydroxylated, instead of being like little steel cables, they end up just collapsing like little noodles. And so when someone has scurvy, they're pretty much melting on a molecular level, because what's supposed to be the strongest connective tissue in their body, holding everything together, is actually melting at body temperature. And so vitamin C is absolutely essential for people's well-being in life. Like any vitamin, it is an essential organic molecule which you cannot synthesize yourself and therefore must get from your diet. And that's what vitamin means. It's a specific organic molecule necessary for human health that you cannot make yourself, so you have to get it from your diet. And if you don't get it, there's a specific disease associated with it. Like if you don't get enough vitamin D, a person will get rickets. Periodic trends. These permit us to predict chemical properties and reactivities of the elements. And we're going into metals, nonmetals, and metalloids. Most elements are metals, and metals are usually shiny. They're lustrous. They're malleable. You can beat them with a hammer. They don't shatter. Their shape will just morph. And they are good heat and electrical conductors. They tend to lose electrons to form cations. Whereas nonmetals are not lustrous. They are not shiny. Lustrous is the special science word for shiny. They are brittle. If you beat them with a hammer, they will shatter. And they are poor heat and electrical conductors. They tend to gain electrons to form anions. And metalloid properties, these have properties in between metals and nonmetals. Some are more metallic, some are more non-metallic, but they're always somewhere in between. And here we see most elements are metals. The easiest way to remember them all is to learn the 7 metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. Are the metalloids. So again, boron, silicon, germanium, antimony, arsenic, tellurium, and polonium. These 7 are our metalloids. Everything to the right is a nonmetal, and also hydrogen is a nonmetal. Everything to the left, besides hydrogen, is a metal. And so if you just learn those 7, you pretty much know literally every single element on the periodic table. They're almost all metals. 7 metalloids and a few nonmetals. So atomic radius. As you go down a group, atoms get bigger. So you'll notice, as we go down a group, atoms get bigger. Why? Because you keep getting more and more energy shells of electrons. It's like building up an onion. As you keep putting layer on top of layer on top of layer on top of layer, you get a bigger onion. As we go right, they get smaller. Because we're getting more electrons, but they're all going into the same valence shell, and we're getting more protons. And so the net result is that there's more protons pulling on the same shell, so that they don't benefit from any screening or anything, and therefore the nucleus can pull it in tighter. And so as you go down, atoms get bigger. As you go right across a period, atoms get smaller, because there's more protons in the nucleus pulling on the same valence electron shell. So as you go down, they get bigger. As you go across a period, they get smaller. Ionization energy. How easy is it to kick off one electron from a neutral atom in the gaseous state? Well, again, as you go down, it gets easier. Same reason atoms get bigger. As you go down, you have more and more bigger energy shells, which means the electrons are further from the nucleus and held less tightly, and it takes less energy to kick one off. As you go right across a period, it generally gets more difficult to kick off an electron, for the same reason that the atoms get smaller. The nucleus is holding on to those electrons a lot more tightly. There are 2 deviations that we see. When we go from beryllium to boron, you see a decrease. Why? Because when you're kicking off one electron from boron, that's 2p. Whereas in beryllium, it's 2s. And it's easier to kick off a p electron than an s electron. And so that's why we're seeing that dip down there, to show that it's easier to remove a p versus an s electron. And then here, from nitrogen to oxygen. This is due to a special stability of a half-filled orbital. The p shell of oxygen, there's 3 p orbitals, and there's 4 p electrons. But if you get rid of one, you actually form an exactly half-filled shell. And there is this very special stability associated with this, and that's why it's kind of beneficial to get rid of that one electron. And that's why you see this dip here. But the general trend is it gets more difficult as you go right across a period, because the nucleus is holding on to those electrons a lot more tightly. Here we see the ionization energies. And you'll notice for lithium, the first one's pretty easy, 520. Then it jumps up to 7,297. For beryllium, 900, 1,700, and then boom, 14,000. For boron, 800, 2,400, 3,600, boom, 25,000. Carbon, 1,000, 2,300, 4,600, 6,000, boom, 37,800. You see a massive jump there, because that's when you switch from valence electrons to inner electrons. And again, the nucleus holds inner electrons so tight, they're not able to participate in any chemistry whatsoever. And you can see how tight they're being held by the huge amounts of energies you would need to even free one. So valence electrons are responsible for all chemistry and all chemical bonds, because the nucleus is holding on to the inner electrons way too tightly. For example, boron, you have 3 valence electrons. We can draw this as a Lewis dot structure. You draw the letter for the symbol of the element, and then dots correspond to valence electrons. Only valence electrons, never inner electrons, just valence electrons. And so as you'd expect, group 1 has 1 valence electron, group 2 has 2, group 3 has 3, 4 has 4, 5 has 5, 6 has 6, 7 has 7, and 8 has 8, except helium. Helium only had 2, but it's still a full energy shell. So draw the Lewis dot structure for the germanium atom. Germanium is in group 4. It'll have 4 valence electrons. Iodine, group 7, will have 7 valence electrons. So all the atoms in this class want to be like noble gases. They will either gain electrons, lose electrons, or if necessary, share electrons to have noble gas-like configurations. And this is the octet rule, because it's super stable. And notice neon, argon, krypton, xenon, radon all have 8 valence electrons. Helium's the one exception, because again there is no p sublevel in the first energy level. And so helium is still a full energy shell, it just doesn't have a p sublevel to fill up. But all the other ones want 8 valence electrons. They have a full energy shell because there is stability in that, and they all want that stability. So in general, metals give up electrons, because sodium is 1s2, 2s2, 2p6, 3s1. But if it gives up 1 electron and just completely sheds the third energy shell, it falls back to a neon-like structure, 1s2, 2s2, 2p6. So sodium plus 1 has the electronic configuration of neon, which is very stable. Likewise, anions gain electrons to get noble gas-like configurations. Chlorine is 1 electron away from being like argon, so it gains 1 electron to become like argon. This is why group 1 always forms +1 ions, because they all have 1 valence electron, and if they get rid of that 1 valence electron, they fall back to a noble gas-like structure. Group 2 always is +2, because if they give up 2 electrons, they fall back to a noble gas-like structure. Group 7 is always -1. If they gain 1 electron, they become like noble gases. If group 6 gains 2 electrons, they become like noble gases. So they're always -2. And group 5 always gains 3 electrons to be like noble gases. And so now we understand the theory of why group 1 is always +1, why group 2 is always +2, why group 7 is always -1. And once you have a sodium plus and a chloride minus, what actually holds them together is the electrostatic attraction between negative and positive oppositely charged ions. And so the ionic bond is not a true chemical bond per se, it's just the natural physical attraction of opposite charges. So in the solid state, sodium chloride packs in an ordered dimension. Each Na plus is surrounded by 6 Cl minuses, and each Cl minus is surrounded by 6 Na pluses. But they're found in a 1-to-1 ratio, so we put the chemical formula as NaCl, 1-to-1.